All right, guys. Well, so I just wanted to start a bit slower today because we sort of rushed right at the end of last lesson, and I just really wanted to make sure that we hadn't gone a bit too quick or lost anyone. So I think it goes without saying, like yesterday we did 4 exercises, albeit it was 1B, but there were 4 components to it. So that's quite a lot. Generally, you can expect from a lesson we're sort of going to be doing 1 exercise per lesson. Okay, although some of the exercises do have a bit more meat to them. So today's exercise, for instance, is going to be 1C, and there's about 15 or 16 questions, I think. So that's what we're going to start. We're going to look at logarithmic functions, and then you have the whole sort of weekend and whatever to work through it to catch up. So in our notes books, we should all be looking at 1C. We're going to go over these questions together. Now, we're going to start with an understanding of logarithmic functions, and we're going to develop that from these 2 graphs here. So let's have a look at the top one. I've got the function y equals 2 to the power of x, and I've also got the function y equals log in base 2 of x. And what we're trying to point out to you guys is that they are the reflection of one another about the function y equals x. Okay? If you're doing spec maths, you're going to learn about the inverse function. They are the inverse of one another. That's the special word we use to describe that. For methods kids, it's just if you flip it around the asymptote, all right, flip it around the line y equals x, you can see that they're the same function. Okay, they're a mirror image. Similarly, all right, we've got in the next, the one below it, e to the power of x. It's not really substantially different, is it? Because remember, 2 to the power of x, that's a function. E is what? 2.72. So we have 2.72 to the power of x. So it's a pretty similar function. And then the logarithm in base e of x, that's ln of x, showing as the reflection of it. All right? So that's logarithmic functions. Now, the very first page I've got here is a recap of exponential functions. We did that in exercise 1A. And the reason we've sort of got a recap of it here is because we're seeing how they're the inverse function of one another, how they sort of map onto one another. So I'm not going to go over too much of this stuff, other than when we get to halfway down, we've got the general form that applies to the logarithmic function. Okay? So we've got y equals a ln of b in brackets x takes c plus d. All right, well, I think we're going to really emphasize when we get to trig how those values affect it. But we've got the dot points there that provide a bit of a summary for us. We've got the shape, which is determined by the a value. And the only other thing to say is that ln of x or log in base e of x, obviously they mean the same thing. For year 12, we almost 95% of cases we deal with ln of x, but if you're solving a logarithmic equation, it doesn't matter if you put ln to both sides or if you put log to both sides, the result is going to be the same. So, we're going to be looking at those points that I've shaded to answer some of these questions coming out. So, we'll flip over the page. We've just got some instructions on how to get rid of logs. So when we're solving logarithmic equations, so I might point to that when that pops up in some of the questions. Let's get into the first one here. We've got an exponential function, 5 take 2.4 times e to the power of x plus 3. So it first says identify the values of a, b, c, and d and describe the translations from the base e function. Graph the function in part b, and then state the domain and range. So we're not going to spend the next 10 minutes going through that because we did this in 1A. So I'm going to leave that one for you guys to have a bit of a go at. I will have a look if you want me to. Okay, that's just an exponential function. We will, however, find the x-intercept exactly. All right? So I want you to think of a graph. It's an exponential function. It looks something like this. We don't really know. We haven't graphed it. It's going to look something like that. Or it could be going down the other way. We don't really know. We could determine that by going through the dot points. But we're going to find the x-intercept. So here's the function. It is 5 take 2.4 times e to the power of x plus 3. And we want to find the x-intercept. The x-intercept, where it crosses the x-axis what happens there? Y equals 0. All right, so all we're doing is we're taking the equation, which is y is this equation, and we make it equal to 0, and we're solving for x. We want to know what is the x value that makes this true. Okay, so we need to break it down, and we're trying to isolate the variable by itself. We need to get the e part by itself. So our first thing to do is subtract 5 from both sides. All right, then we're going to divide both sides by minus 2.4. Alright, and that you could evaluate if you want to. When I'm doing these kind of problems, I'm just like algebra, like you just do the maths with, with your pencil, and then put it in your calculator at the end if you need to. The reason is if you stop here and then you put it in your calculator, it can slow you down a bit. Alright. So we're trying to solve for x, right? We've broken it down, we've isolated. This is the variable term, but we still need to get rid of this e. How do we get rid of e? We put ln on both sides, okay? ln of e to the x plus 3 is equal to ln of 5 on 2.4. Alright, so we've applied the natural logarithm to both sides. One of the laws we saw last lesson, ln e to the x simplifies to x. Therefore, ln of e to the x plus 3 simplifies to x plus 3. And then take away 3 from both sides. We've solved for x exactly. What's that number? 2.4, isn't it? 4, 4, and take away 3. All right, and from there, we've got the exact solution. That's the exact value. That includes every possible decimal point. We could go through and solve it to 3 significant figures by evaluating in our calculator. Another way we could obtain it is by graphing this function and g-solving the x-intercept. That's how you can verify that you've done the correct process, right? Okay, so there's that one. And then we will do find, so I might leave this one for you guys as well. It says find the value of x when y is 2.3, because you're actually going to follow a very similar process. All you're doing, so that's for part E, we have 5 take 2.4 times e to the power of x plus 3. That's our function. When the y value equals 2.3. Okay, so it's pretty much the same process, except we've got 2.3 over this side instead of 0. So that's a good opportunity for you guys to practice that skill independently. Okay, so that's exponential functions, and the only extension we've done there on 1a is to look at how we can find x-intercepts and corresponding x values given a y value manually, how we can do it using a manual process. So let's get on to our logarithmic function then. We have question 2. Y equals log in base 5 of x plus 3 take away 2. Log in base 5 of x plus 3 take away 2. Identify the values of a, b, c, and d, and describe the translations from the base ln function. So we're going to be comparing that to, we have to flip back a couple of pages. On page 13, y equals a ln b of x take c plus d. All right, we're comparing this function to this function. All right, don't be confused by the ln. The ln just means log in base e, right? So there's the same properties still apply. So we're going to say what corresponds with a. What's this number out the front? A equals 1. All right, there's an invisible 1 there. We don't need to write it. It's redundant. And this is the dilation factor. So there's no dilation or compression from the standard log function. So we can write that. No dilation or compression from the standard logging base 5 of the x function. All right, if we had a equals 2, then it's stretching it by a scale factor of 2. If we had a equals 5, it's multiplying every value by 5. If we had a is half, it's halving every value. All right, so that's our dilation factor. Next is b. And b, it's outside the bracket here, but really the point of b is that it's the coefficient of x. What's the number in front of x? All right, 1. B is 1 as well. And that's going to be the horizontal dilation factor. So again, because it's 1, no dilation, we can write the same thing. Okay, then we've got some horizontal translation. So look here, we've got x takes c, and over here we've got x plus 3. So therefore c has to be minus 3. Okay, if you take minus 3 and you put it in here, you're going to have x take minus 3, which simplifies to x plus 3. Okay, and we should remember when we have x plus c, it shifts it 3 units to the left. Okay, x plus c left, x takes c right. So shifts the standard log in base 5 of x function 3 units right out there. And then d minus 2. D is our vertical translation. So we have the function, we're evaluating it, and then whatever the value is, take away 2. Okay, whatever the y value is, take away 2. It's shoving every y value down. D is minus 2. Shifts, mine's going to be right, yep, log in base 5 of x down 2 units. Picks it up, drops it down 2 units. Okay, so that's part A. Part B, graph the function. Let's do that on our calculators. And we'll get all the information we can. So, just to recap what I was talking about to you yesterday, I was showing you how we can sketch or how we can calculate log in base A. So we go option, count, log AB. Option, count, log AB. There it is, it pops up for us in the graph menu. Okay, so we're going to graph the function y equals log in base 5 of x plus 3, take away 2. So we can just put all of that information in there. So 5 is a little subscript, we have x plus 3 in the brackets, and then we have a take 2 hanging out outside the brackets. I've got like 7 functions in here. Just go to V window standard for now. And if your calculator's popped out anything like mine, if you've set it as standard, it should look pretty well the same then. It sort of looks like it starts here and goes like this. Okay? Now what's going on there is we actually do have an asymptote, alright? And it's not heaps clear from the graph. This is where the technology can be a bit faulty, and that's because the calculator is achieving an error as it's trying to calculate the limiting value. So what we'll do is we'll look at our notes to determine what is the value of the asymptote, where does it occur. So let's flick back again on page 13, have a look at the dot points. C is the horizontal translation, and hence x equals c is the vertical asymptote. Okay, what's our value of c? Oh, minus 3. Excellent. So that means we have an asymptote here at x is minus 3. And if you trace along the function, it'll go, you get here, you go 2.8, 2.9, 2.99, error, does not exist. So we have a vertical asymptote at 2.3, and we can't see the x-intercept yet. There will be one somewhere because it's going that way forever. So that's a suitable graph at this stage. We're relying on our calculator to help us generate it. Okay. Alright, so the next part says, state the domain and range. Okay. So, if you think, we've got arrows there and arrows there. Think back to an exponential function. an exponential function had a domain that went forever. If we perform the inverse function, which is the log, it's going to have a range that goes forever. It's going down and up forever. So for our range, let's answer that one first. We're just going to write YER. That is, Y, the Y values, belong to, obviously, E means belong to. Not real obvious, is it? But that's what the mathematical notation is. Y belongs to the set of all real numbers. It exists for every possible real number. Okay, X on the other hand, all right, we can determine from our graph, we can determine from our dot points, X exists for values larger than -3. Okay, doesn't exist at -3, doesn't exist for values less than -3, only values that are larger than -3. Alright, so we're getting through them. State the domain range. Find the y-intercept exactly. So, let's see if I can get some space here. You want to see the razor? Or a swab? Here's one. It's not real big. Okay. So, the y-intercept. Find the y-intercept. Again, if you think about our graph, all right, x-intercept occurs when the y value is 0. Y-intercept occurs when the x value is 0. All right, so all we're doing is putting x is 0 into our function. Y-int. So we can make the statement occurs when x is 0. Logging base 5 of 3, take away 2. We can evaluate that to a few figures. We can g-solve it from our calculator. There's ways of determining it. This is the exact value. Okay, that's what it is. Exactly includes every possible decimal place. Find the value of x when y is 2.3. So here's the function, y. And we want to know what's the value of x when it equals 2.3. Equals 2.3. So we're trying to solve for x. We want to break it down. We want to get x by itself such that the function is the y value equals 2.3. So, step 1, let's try get the variable by itself. We're going to add 2 to both sides. That's how we get rid of that one. Okay. Now we have log in base 5 of x plus 3. So you might remember yesterday, we were doing some equations like this. Ln of x equals 2. How do we get rid of ln x? We put e to the power of both sides, right? And that makes it x equals e squared. E to the power of ln x simplifies to x. So over here though, we've got log in base 5 of our variable. How do we get rid of log in base 5? Okay, so that's why I've written that table. That's on page 14. Okay, how to get rid of logs. So if we've got ln of x equals 2, we put e to the power of both sides. If we've got log of x equals 2, we put 10 to the power of both sides. Why is that? Because it's base 10. What about in the first case? Because it's base e. Here we have log in base 5 of x plus 3. How do we get rid of log in base 5? We put 5 to the power of both sides. Okay? So what that's going to do is it eliminates the log component of the expression. So we're left with x plus 3 equals 5 to the power of 4.3, and then we'll subtract 3 from both sides. Okay, so we've determined the x value exactly when y is 2.3. Alright, and we will do this one. Actually, what do you guys reckon? Do you want to do it now or when we come back from recess? It's still 10 minutes, so we could do a bit or... Yeah. Do you Do it now? Let's do it. Yep. Pretty cool. All right. I'm just mindful. I just don't want to rush ahead and lose people. But yeah, let's do it now, and I'll just look around and inspect the lesson. All right. So we have the function y equals 3. Take ln of x take 1 to the power of 5. Identify the translations from the base ln function. So that means identify the values a, b, c, d, and that's all. All right. Can anyone see what a is? It's discrete, it's hidden. It's not 3, it's not -1.
5.
It is 5, yeah, very good. So this, we could rewrite like this. Okay, remember if there's a power there, we can bring that out the front of the ln function. So then the value of a is, it's not 5, it's going to be -5 is, because we consider, is it positive or negative? That's going to dictate its shape. It's going to be a downwards log function. Go through, we'll crack out b. B is 1, c is, it's moving, c is 1, and d is positive 3. So we've got A, B, C, D. Doesn't ask us to comment on them, just says identify the translations. So there we go, that's fine. State the domain and range. Okay, so for all logarithmic functions, range, yeah. Okay. I've got lots of good jokes like that, so listen carefully. And for the domain, all right, it exists for all values larger than c. All right, so it's going to exist for all values of x greater than positive 1. All right. C. Find the value of y of x when y is -5. So we'll do that one here. We have 3 take 5. I'm going to treat it like this. It will work the other way as well. 3 take 5, ln of x take 1 equals -5. Okay, solve for x such that this y value equals -5. So yeah, you can still do it with the 5 up here. I've brought it down the front just because I think it's going to be easier. We'll just smash it out straight away. So first thing we're going to do is get rid of this 3. Take away 3 from both sides. Divide both sides by -5. How do we get rid of ln? E to the power of both sides. Okay, the base is e, so we put e to the power of both sides. Brackets now. So therefore x is e to the 8.5 plus 1. Very good. Alright, so we might have that discussion down the bottom towards the end of the lesson. Now, so up to you whether you want to go through and have a go at that exponential problem that we didn't fill in at the start, or if you want to continue with exercise 1C. We've got about 5 minutes till recess. There we go.